Hi, in this video I will go over maps and answer what is a map, when do we use maps, as well as how do you use them, and some practice using map operations in C++. So first, what is a map? It is a data structure. Like the previous data structures, it is used to basically store a collection of elements and provide us with operations that we can use to manage those. And an example of a map is, let's say we have a collection of students in a class. Let's say we have 20 students and we want to store their grades. So we have on this side the students, and it's all names here, and then we have the grades, which are all numbers here. In maps, we can store key value pairs. So each student and their grade are going to be a pair that's going to be stored in the map. And each pair does not need to have the same type for their keys and values, which is a good thing, because in this case we want the students' names to be of a string type and their grades to be of an integer type. So the pair is going to consist of key of type string and a value of type int. And this is just to explain it. This is not the syntax of how to initialize it, but that's basically what maps are useful for. And they come with operations that are efficient to handle key value pairs. So we have two types of maps in C++. The map, which is just the map by itself, it comes ordered. So elements, when you insert them, they get ordered by key. In this case, the students are going to be ordered lexicographically based on their value, the value of their characters, and it's going to be like in alphabetical order. But in unordered maps, elements are not going to be ordered. So one thing to note about maps is that they're implemented using binary search trees in C++ standard template library. And another thing about maps is that the keys are usually simple type, but the value can be something more complex. Like, I'll give you an example. The key could be just a string, as we said earlier, and the value could be a list of multiple values, which is useful in some cases where you have to store more than one element for a key, like different grades for the same student. Okay. Maps, usually in other programming languages, we have hash maps, which we're going to talk about briefly, because in C++, unordered maps are implemented using hash tables. So we use a hashing function. Basically, it takes in the key goes through this hashing function, and we get a code, and that is used to determine where the key value pair is inserted into this map or unordered map. And one thing to note about hashing is that in user-defined types, we need to have our own hashing function. So let's say you are using unordered maps and you're inserting elements of the types that are provided in C++, then it's going to be fine. Those elements are going to go through this hashing function and they're going to be inserted into this map. But then if you're inserting user-defined types, then you need to create a hashing function that's going to handle this inserting. And what do we use hashing for? Hashing allows us to insert elements in a way that we can also find them very quickly using this code. So if you hash the same key multiple times, you're gonna get the same code. So it has consistent behavior. Another thing about maps are collisions. So collisions happen when we have multiple keys, two or more of the same value. Let's go back to the example of the students. Let's say we have two students with the name John, like same exact key. They both have the same key and they have different values. So this John has a 90, the other John has an 85. After we insert the first one, when we try to insert the second one, we're gonna have a collision because remember the hashing, it produces one code for each unique key. And the collisions are handled differently depending on the map's implementation, underlying implementation. So there are ways like chaining or linear probing and other different methods that, depending on the implementation, they handle those collisions. But before you start using maps, it's important to note that a collision leads to the worst case time complexity. This means that usually operations in maps, we're gonna see them in a second. Let's say in maps, the ordered ones, on average they take big O log of n. As you can see, for most the operations. However, if we have a chaining case, we're gonna have a worse time than this because imagine we had the John twice with different grades. Then one approach is to create a linked list to store those values. So this would cause us to more either time or space complexity. So I'd recommend you learn how collisions and hashing work on more detailed. But before using maps or unordered maps, it's important to know that about this certain behavior. So now let's look at the time complexity. Again, we have maps and we have unordered maps. Maps, on average, take big O log of n for inserting, removing, accessing, searching elements. And that is due to the binary search tree implementation. Which is why I prefer to use unordered maps when I don't need the element to be ordered, at least, because the operations only take big O of 1, which is constant time and much more efficient. Unordered maps are implemented using hash tables, and again they use the hash function to map keys to indices in an array. This is basically how it works in its implementation in C++. Okay, so now how do we use maps? The first step is to include the map standard library template, which is by following way. In this line we include the map, and the other line we include unordered underscore map. And after this you can basically declare them using this map keyword and unordered map keyword. So first comes the map keyword, and then in those two signs we indicate the type of the key and the value. So we're saying that we have a map of key type string and value type int called m1. and here we have the same thing called M2, but this is an unordered map. And now we can start performing operations on those maps. We're going to look at inserting, accessing, searching, and removing elements, as well as some other operations. So M1 was our ordered map, which is just map. The way we insert an element is by using this insert operation with those two parentheses. Inside we indicate the type of the pair, so we use this pair keyword, and again those signs to indicate the type, and between those other parentheses, this is actually the key and this is the value that's going to be inserted into the map. I think there's different ways to insert elements, but this is the one I use. And just a note that this has to be consistent with the one you initialized here, because elements have to be of the same type after you declare the map and what the key value pairs are going to be. You can index into the key to reassign the value. Let's say we have M1 and here we say Joe. You can say is equal to 85, and now the value of Joe is going to be 85 instead of 90. This is a way to reassign the value. And indexing works because if you remember here we're using arrays in the underlying implementation for unordered maps at least. So how do you access elements? You can use the indexing, so M1 and then square brackets key Joe would return 90, which we're storing inside this value integer type. You can search through this find function. The find function returns an iterator to the key value pair. So if we try to find Joe in M1, which exists, it's going to return an iterator which we can dereference to get the value of either the key or the value. We already know the key, so in most cases it's going to be used to get the value. When we do not have, let's say we're trying to find Alex, and Alex does not exist, it's going to be equal to the end of the map. It's going to basically point to it. So we're going to look at the code to explain this in more details, but this is the find operation is very useful, and it's only constant time like the other ones here. We can remove elements using the erase operation by just passing in the key. And we have other operations like count, size, and clear. And this is how you iterate through a map. We have this pair. For each pair in M1, we store the key and the value in those. So pair dot first gives us the key of the pair, and this is the value of the pair. So again, M1 is a map, and pair is the pair object, which includes both the key and the value. So for every pair in M1, we can get the key through pair dot first and the value through pair dot second. And we always use first and second. Let's say we have this is pair 1. For pair 2, we also do dot first, pair 2, dot second to get the key value of the second pair. And you can also iterate using this way by using the begin. And yeah, this is the when it's not equal to end. So when an element is not found or we reach the end of the map, then basically we reach the end here, and you can dereference them the same way. Dereference the iterators to get the first or the second instead of getting them through accessing them here you point to the first and the second, and you would get the key and the value actual elements. So now let's look at the code. Here we first include map and unordered map. We initialize this map, type string, a key of type string and value of type int called map1, and we insert a bunch of elements in here. We have cake, cookies, donuts, brownies, and pie, and corresponding to those values are a count of type integer. So we have 5 cakes, 3 cookies, 2 donuts, 4 brownies, and 1 pie inside this map. And then try this and run it to see what the output looks like. Here I'm iterating through the map and printing the first and the second, and what this does is basically give us the lists. So cake 5, we insert those elements, but then the output comes out ordered, because remember we're using a map. So, and it's ordered by the key. So in this case, cake is gonna still be brownies are gonna be first. So I'd recommend you run this to see how it actually outputs. When I ran this, I got brownies, then cake, then cookies, then donuts, then pie. And this is how you reassign the value. I'm reassigning the value of pie to 10. I just bought 9 more pies, and if you print it, you're gonna get the new value as it's updated. And yeah, I used the second way of iteration to show you how the pie value gets updated. Now let's look at unordered maps. I called it map2, and it also has key of type string and value of type int. I am inserting the same elements here, and when I iterate through them, they're gonna come out in some random unordered order. So it's not guaranteed they're gonna come out like this, but their operations are more efficient, which is why I prefer them. So here I'm showing you how to use the find operation, which is interesting. It returns an iterator to either the pair or to end. So in this case, find pie, I can use this conditional statement saying if the iterator is not equal to map.end, then I'm printing it. And this can be used to know whether pie exists or not, because the find pie, it basically returns one of two things. Either map.end, so it either points to the end of the map, or it returns or it points to the actual pair, and then you can dereference it by using this to the first, to the key, and here to the value. And yeah, this is how you iterate. It's the same as maps. Unordered maps, they work the same. And one last thing I wanted to mention is the multi-map, which is a third type of maps. It's not very known or useful, but the only key feature about multi-maps that I found important is it allows you to insert multiple elements with the same key. So as you can see in this case, I have the same elements plus pi inserted twice. Remember, in a normal map this would cause a collision, but in a multi-map it would actually allow us to insert both of those with their distinct values, no problem. And yeah, if you want to try it and iterate through it, you're gonna see the output's gonna include all those elements.